Hi guys, so today we're going to be learning grade 10 unit 2, substance. So substance first of all classified into two. But first of all, substance is anything or it's any physical thing. So we're going to be classifying it into two. So pure substance and a mixture. So pure substance are further classified into two also. The element and a compound. So pure elements are fixed composition. They cannot be separated by any physical or something like that. So elements and compounds. So elements are that cannot be broken into simpler components. For example, sodium chloride. And the compounds are chemically bonded, and they have fixed proportion, and they have a unique result. Like we cannot retain their property by physical process. And in other hand, we have a mixture, which is a homogeneous mixture and a heterogeneous mixture. So homogeneous mixture are a uniform substance with no visible boundary. So on the other hand, they're heterogeneous. So heterogeneous are substances which have a visible which have visible boundaries, and mixtures in general they are heterogeneous except that of solutions and alloys, and they have variable proportions. They are physically combined and regain their property and can be separated physically, and they can retain their properties physically. And a key property or a key thing that what we need to know is that all solutions are homogeneous mixture, but not all homogeneous mixture are solutions. Like a pure substance is also uniform, so we cannot say that all homogeneous mixture are solutions. So in solutions are like they can be classified into three ways, like the liquid, gas, and solid solutions. So if we see on the gas solutions, if the solvent is going to be the major gas. For example, like in our atmosphere, the most abundant element, pay attention here, the most abundant element and the most abundant gas have a different things. Like mostly in exams, that's what makes students get confused and make the same mistakes and again. Like, which one of the following is the most abundant gas? It's going to be like A, nitrogen, B, oxygen, C, carbon dioxide, and many other more. So what we know is that the most abundant gas is nitrogen, right? So we're going to be saying A. That's correct. But another teachers will make the question trickier and make that the most abundant element instead of a gas. So A is nitrogen, B is hydrogen, C and oxygen. Which one is the answer? The answer is not an A, it's B. Hydrogen. Hydrogen is the most abundant element. So back into our topic, in a gas solution, the major gas is going to be the solvent, and the solute is going to be the minor one. So the major one is the nitrogen, and the other one's the minor solid solutions. That's what we called gas solutions. And looking at liquid solutions is that anything that's solvent in a liquid is a water. So if the solvent, if there is a substance is combined with the water, so we're going to be knowing that the major one is the water, but in liquid both of them are going to be a solvent, but we're going to use a larger proportion of water. And the last one is a solid solution. So in solid solutions, the best example for this one is an alloy, which have less impurities than ore. And there is also a solid liquid solution, which is actually used in densities. Like in our tea, there is an agar solution, which contains a silver and a mercury. A mercury is a liquid and a silver is solid, so it's going to be a solid liquid solution. So this solution is also is mostly used by dentists and in the medical field. And back into this one, our third topic is going to be the suspensions and colloidals in a solution. So solutions are homogeneous, they do not have a tidal effect, and suspension are particles, but those particles settle over time. For example, a muddy water, they have a visible boundary and a subtle. And the colloidals are heterogeneous reactions, heterogeneous mixtures, and they are quite stable than suspension, and they do have a tidal effect. For example, a milk and a fog. And to get here in this one, solutions are the most stable. They cannot be fertilized even by tiny filter, and colloid suspensions can be filterized, but colloids cannot be. So here's what I wrote in a rate. Filtration work is for suspensions, but not colloidals or solutions. So colloidals are quite stable than suspensions. That's why they cannot be filterized. And a solution, even by the smallest pure of filter, it cannot be. So our fourth step is going to be like dissolves like rules. So basically, polar dissolves the polar molecule, non-polar dissolves the non-polar molecule, and not all you need to know. And for the intermolecular forces, I made about intermolecular forces and intramolecular forces in my another video. You can check it out. But we're going to be seeing it in clear way here. So there's an order for them, which is the most strongest one, which means ion dipole and hydrogen bonding, and a dipole and a London dispersion force. The London dispersion force is an intermolecular force, which is the weakest one, which is actually for example, like in alkanes. Alkanes mostly are London dispersions for, like most of them, like all of them are London forces. Like, to know better about those intermolecular forces, you better check out my another video about those things. So I'm going to make it pin on my description list. And we're going to be talking about solubility rules in this chapter. So in this chapter, like in this video, I'm going to talk about the most key points that you need for your entrance exams. Like for grade 12 students, you're going to be learning those backing. Like, that's why I'm making this video. And for those who are in grade 10 still, you better learn it better in my another video. I have more intermolecular forces. And for those grade 12s, those are the key points you need to check out better for your entrance. And about solubility rules, I'm having a trick here. We're going to be using a trick. You don't learn all of the things that's in book. Like, don't read all of them. Let's use a trick here. So I'm going to use a nag sag. Don't always nag your pants, because people are gonna don't sag your pants because people are gonna nag you. So what does that mean? Nag, sag. Nag. Let me do the packer and nag, sag. They are always soluble. Nag, sag. N is for ammonia. A is for acetates, which is C2H3O2. Oh, this one is not bolder, so let's make it in a black. And G stands for the group 1 metals, which is sodium, lithium, potassium, and goes on. And S for sulfates. And A for N for nitrate, which is NO3. sorry for my mistake, and A for ammonia we're going to be using here, just to be make it order. That's why I cancel that out. And G for the group 17s. You can also use another trick, which is NASA 17. But I prefer this one, nag sag. Don't sag your pants because people are gonna nag you. So group 17s are that of fluorine, chlorine, and bromine, and goes on. So those are always soluble, but when I say they are always soluble, I lie, because there is an exception. So here we go again, it's chemistry, there's exceptions. So I'm going to use another trick for this one, another word, which I call PMS, which is lead, mercury, and silver. And another exceptions are castor bear. The reason I called it a castor bear because it contains calcium, strontium, and barium. It's called castor bear. So I say those are always soluble, but the exception is when the sulfate groups come with those PMS and the castor bear. So when they come with those two groups, they are insoluble, always insoluble. So another exception is for the group 17s, which is let me use another one. The group 17s, when the group 17s come with those PMS, they're going to be insoluble. So that's the trick. Memorize it for your entrance exam. That's why I told you don't need to read all of the things that is in book. Just use the shortcut. Like as they say, the legendary says that study smart, not hard. And what we're going to be seeing is that another thing here, which I stated in here, oxide groups. So oxide groups are always insoluble, except with group 1. And the carbonates, phosphates, and silicates are always insoluble. Exception is that when they come with those group 1. So when you see those three elements, those three compounds with the group 1, they are always insoluble. They're always soluble when they come with those. And hydroxide ions are always insoluble, but when they come with the group 1, they're always soluble. And another concept we're going to be seeing is in this chapter the energy and rate of dissociation. This is actually also stated in the grade 12 unit 4, which is in the chemical kinetics. There are a lot of factors that affect the rate of dissociation. You're going to be seeing it there, but I'm going to tell you shortcut here too. So the rate of dissociation is actually just like how something is dissolved in something, right? So for example, when you increase the temperature, will the water boil or not? Yeah, it will boil. So which means that the rate of dissociation is increasing. Like if you boil something, not a water, but something another thing, like for example a food, if you increase the pressure for it, it's going to be increasing the rate of dissociation. So that's how it works. And if to increase the rate of dissociation, if you need to increase the surface area. If you give something if you give something enough space for it to dissolve, then you're going to be increasing the rate of dissociations. So surface area have a direct relationship with rate of dissociation. And another thing is that the intermolecular the interparticle mass. So if the interparticle is larger, which means if you increase the interparticle, then the rate of dissociation is going to be decreasing, because we need more energy to dissociate that one. So they have reverse, I mean, they have reverse relationships. And to break down solutes, so in energy and rate of dissociation, what we're going to be seeing is that the concept of solvation. Solvation is when the solute particles are surrounded by solvents, that solvation happens. So to dissociate things, first we need to break down the solute particle, which is an endothermic. And to break down the solute solvent, we're going to be using endothermic. And our third step is to form a solute solvent forces, which is a solvation or hydration exothermics. So hydration is an exothermic, which is the energy that we're going to be using to form ions apart, right? Because it's exothermic, we're going to be using that. And hydration energy and a lattice energy. So lattice energy works to oppose hydration energy. So lattice energy and hydration energy are reverse. So lattice energy is the energy that is required to binding up ions. Another thing, a lattice energy is also used, the energy that is used to break down ions apart. But in this case, lattice energy can also be, in some cases, binding up in ions, and hydrogen energy is going to be making to separating those sides. And usually in exothermic, so heat is released when a water molecule completely surrounds a solid particles, because it's releasing energy. And this break of the lattice is an endothermic process. And hydration of ions favors the dissolution of an ion or ionic solid in the water. This lattice energy works against the solutions process. So an ionic solid with a relatively large lattice energy is usually insoluble. So lattice energy depends on the charge of the ions and also the distance between the particles, which is actually the usual formula, which is K is equal to, the lattice energy is equal to KQ1 Q2 over R squared. That's how you're going to be calculating the lattice energy in some points. I'm going to make another video on this cases, on this concept, And there is another concept in this chapter, which is saturation and equilibrium. So in saturations, it is about how a solution are in a particle, which means that if the solute and the solvent particles, how the solute and solvent particles are like dissociate. For example, unsaturated solutions are a solution which have a low solute, and if you add more solid on it, you're going to be dissolving. And saturated solutions are with the rate of dissociation equal to the rate of crystallization, which is, we call it a dynamic equilibrium. So in this case, if you add more solid, is not going to affect. It's not going to be dissolved further because it's already at equilibrium. And the supersaturated solutions are high temperature and pressure. We're going to be forming that, which is when the solute particle is beyond needed for to be dissolved. And if we cool this supersaturated, is going to become with what is known as metastable state. And another concept is that most solids increase their solubility as temperature increase, but gases solubility decreases as the temperature increases. Why? Because gases have a depression force, which is the weakest intermolecular force. I make it a video on this one. You can check it out when you check out the intermolecular forces. And so gases have actually the weakest molecular bonds, which means their particles are further apart that even the intermolecular is nearly zero. It's actually zero. So that's why if you increase the temperature, it's not going to have any effect on it. But if you increase the pressure, yeah, it might be, yes, it's going to be increasing the solubility. That's how we're going to be seeing in Henry's law. And for example, a Coca soda holds more fizz. Now we're going to be seeing it in Henry's law, which is I have written here. So Henry's law of gases. So the law is C is equal to Kp. K is Henry's constant, C is solubility, and the P is pressure. So solubility and pressure have a direct relationship. That's what I said. In a gaseous particle, if you increase the temperature, it doesn't have any effect. But if you increase the pressure, it have. That's why the solubility and the pressure of a gases have a direct relationship. This only works on the gases, not on solids, not on liquids. So NT is total solution. So then another thing is molarity. Molarity is mole over volume. We're going to be using it capital M. Molality is mole over kilogram, which is small m. And normality is molarity times equivalent. Equivalent is an ion. For example, HCl, if we see the hydrochloric acid loses 1 electron, so Z is going to be 1. And in sulfuric acid, the Z is 2. And in calcium hydroxide, the Z is 2 also. In ammonium sulfate, the Z is going to be 6, which is aluminum is 2. And its valence electron 3. 3 times 2 is 6. That's what we call the equivalent. So basically, those are the basic things that you need to know for your entrance exam. Those notes are enough, more than the book. And to be clear, use this trick. Always is going to be helping you in your exams. So thank you very much. Your comments might lie. Use those tricks and ace your next exam. Bye.